Welcome to the Getting Started with GeoStudio video series. This tutorial guides new users through the basics of creating a simple seepage analysis in SEEP. This video will cover how to set up the properties of a SEEP analysis in the definition view, use the Solve Manager to solve the numerical analysis, interpret the solved analysis in Results view, and view and print the analysis in page layout mode. The project definition involves selecting the basic analysis properties, drawing the model geometry, creating and assigning material properties, and defining the boundary and initial conditions. This tutorial considers steady-state seepage through an embankment dam comprised of a single material. The upstream reservoir has a constant head of 11 meters. Seepage may leave the dam along the downstream face, and we will create a second analysis to consider the influence of a tow drain on the downstream side of the dam. We will begin on the GeoStudio Start page. Here you can create a new project, open an existing project, or click on the appropriate links to view the examples, tutorial videos, or engineering books for each GeoStudio product available on the GeoSlope website. When creating a new project, you can select the default units and project page size from a range of standard sizes. After clicking on the New button, I will select the metric units with a letter size page and create an analysis. Once the new project is created, the Define Analyses window opens where we can edit the title, specify the author, or add comments for future viewers. Under the Settings tab, we can change the viewable units or set a project start date, which is useful for SEEP models including climate data. We will add a steady-state SEEP analysis to the analysis tree and change its name to 1 Steady-State Seepage. We may also change the analysis type to transient or add a description about the analysis to help future users. In the Physics tab, we can select additional mass or heat transfer processes. In this case, we will only model groundwater flow due to pressure and gravity-driven gradients, which are the default physical processes in SEEP. Next, we will look at the Water tab, which contains the convergence criteria for the analysis. Here we can change the maximum number of iterations, the iteration comparison criteria, or the under-relaxation criteria. A separate tutorial video is available with a detailed description of the convergence and under-relaxation scheme. Under the optional processes, we may also specify the unit weight of water and the bulk modulus of the pore fluid. The Settings tab allows for the selection of the analysis dimensions, which we will leave as two-dimensional. The Time tab can be used to change the time steps and duration of transient analyses. As this is a steady-state scenario, we will keep the default starting time and duration as 0 seconds. We are currently in the definition view of our analysis. The red and green lines in the model space represent the X and Y axes respectively, and the grid is activated. Both of these may be turned off by going to View Grid. The grid spacing and snap to grid option may also be modified here. The base units of the analysis are found under View Units. Both the base units and the derived units may be modified. However, we will use the default units for this analysis. The zoom options along the bottom bar of the screen provide various options for adjusting the analysis view. We can also go to View Zoom to change the display scale and current zoom percentage, or zoom to the extent of the model domain. We can add axes to the working area to help visualize the drawing extents of our domain. Under Sketch Axes, we will specify the titles for each axis, as well as the X and Y axis extents. The X-axis extent will be 55 meters, and the Y-axis extent will be 12 meters. You can also modify the axis increments by toggling off the Auto Increment Size button and changing the increment size for each axis. Let us now set up the domain geometry. There are several methods for drawing the model domain. First of all, we may import regions from DWG or DXF files, or from other GeoStudio files, by going to File, Import Regions. We may also import a drawing under Sketch, Pictures, scale the drawing to the model domain, and use it as a reference for creating the desired regions. Alternatively, we can copy point coordinates from another GeoStudio file or from spreadsheet software like Microsoft Excel and paste them into the Define Points window. Finally, we can draw regions by going to Draw Regions. Let us use this last option for defining our embankment geometry. In the Draw Regions window, ensure the polygonal region type is selected. Points are automatically generated when we click on the working area, and lines are created between these points. We may also enter point coordinates in the coordinate entry box at the bottom of the window. To stop the Draw Regions command, click the right mouse button or press Escape. Additional points can be added to the domain if required. We will add a point along the upstream face of the dam at the reservoir water level. This point divides the upstream dam face into two lines, ensuring that the boundary condition representing the reservoir will only be applied to the bottom portion of the embankment face. The sketch tools may be used to draw geometric shapes to help us visualize various aspects of our problem. For example, we can use the Sketch Line button to draw the reservoir water level. These sketches are not included in the domain or the analysis and can be moved, modified, or deleted using the Modify Objects command. After defining the model geometry, the next step is to create and assign the material properties. To establish the material, we will go to Define Materials. We will click on the Add button to create a new material, give this material a name, and select the Saturated/Unsaturated material model from the drop-down menu. A saturated-only material model can be used when the domain remains saturated for the entire duration of the analysis. In this example, we expect that only part of the domain will be saturated, and so we must use the Saturated/Unsaturated material model. The Saturated/Unsaturated material model requires hydraulic conductivity and volumetric water content functions. Clicking on the ellipses button beside the volumetric water content function opens the function definition window. In GeoStudio, the ellipses button typically indicates that additional features are available. In the function definition window, we will add a volumetric water content function, give it a name, and select the volumetric water content data point function type. We can use the internal estimation algorithm to generate the volumetric water content function by clicking the Estimate button. The sample function's estimation method creates a typical volumetric water content curve based on published literature, given the soil type and saturated water content. We will use a saturated water content of 0.5 and choose the silt sample material. After pressing OK, the estimated function appears in the graph window, and the corresponding data points are listed in the table. If desired, the Edit Data Points option can be activated and data points within the curve can be deleted, moved using the left mouse button, or edited manually within the given data point list. Points for the curve can also be added by pasting the points into the data table, provided the appropriate columns are copied from a program such as Microsoft Excel. The curve properties may be modified using the Curve Fit and Segment scroll bars, which may be useful if the curve of the function does not pass through the desired data points. Beta, or the coefficient of compressibility, will be set to 5 × 10⁻⁴ per kPa. We will now close the function definition window and select the developed function from the volumetric water content function drop-down menu. Next, we will specify the hydraulic conductivity function in a similar fashion. First, click on the ellipses button beside the hydraulic conductivity function drop-down menu. Add a new function, change its name, and select the data point function type. Similar to the volumetric water content function, we can use an internal estimation algorithm to create a hydraulic conductivity curve by pressing the Estimate button. Select the Van Gunsten estimation method and choose the volumetric water content function we just defined from the drop-down menu. We will set the saturated hydraulic conductivity to 1 × 10⁻⁶ meters per second and the residual water content to 0.05. Again, we can choose the Edit Data Points option to modify or add data points. The hydraulic conductivity function definition is complete, so close this window and select this function from the drop-down menu. For anisotropic materials, the Ky/Kx ratio may be modified so that the hydraulic conductivity is different in the x and y dimensions. A value of 1 indicates that the vertical hydraulic conductivity is equal to the horizontal hydraulic conductivity. If the material had a vertical hydraulic conductivity that was 1/10 the horizontal hydraulic conductivity, this ratio should be 0.1. The rotation option allows you to shift the xy planes in which the anisotropy occurs when they are not purely horizontal and vertical. Lastly, the activation pore water pressure option allows you to choose a specific pore water pressure for the entire material when it first becomes active in the simulation. The material definition for our embankment is complete, so we can close the Define Materials window. Now we will add the material to our domain by going to Draw Materials, selecting the embankment material, and clicking on the region. Creating and assigning boundary conditions is very similar to creating and assigning material properties. Under Define Boundary Conditions, we can see that 2 boundary conditions are automatically generated. These are the potential seepage phase and zero pressure boundary conditions. The potential seepage phase boundary condition is available for external nodes where a seepage phase may develop. The solver uses an iterative procedure to locate the nodes where the pressure is greater than 0, reassign the pressure at these nodes to 0 kPa, and determine the corresponding flow out of the domain. The zero pressure boundary condition applies a constant pressure of 0 kPa or a constant pressure head of 0 meters at the chosen nodes. We must add a new hydraulic boundary condition to represent the reservoir level in our analysis. We will set the new boundary condition to a constant head of 11 meters. We can change the color of the boundary condition by clicking on the Color Set button while the item is active. Now we can open the Draw Boundary Conditions window. We will select the reservoir head boundary condition and apply it to the upstream face of the dam where the reservoir is present. We will then select the seepage face boundary condition and apply it along the downstream side of the embankment to allow water to exit the domain if the pressure exceeds 0 kPa. Boundary conditions may also be applied to regions and points, depending on the requirements of the analysis. The last step of developing our numerical analysis is to view the finite element mesh by going to Draw Mesh Properties. Here we can see that the default mesh is set to have an approximate global element size of 1.5 meters. We will create a finer discretization for the global mesh by changing this value to 1 meter. Mesh constraints can also be applied to individual regions, lines, or points, but it is recommended to start with a simple mesh. Now we will ensure the analysis is activated in the Solve Manager window and solve the analysis by clicking on the Start button. Once solved, the window will automatically change to the results view. By default, the flux vectors appear once the analysis solves. The blue shaded area represents the reservoir head level applied on the upstream face of the dam. The Results Times window provides a list of the solved time steps, allowing you to view the results for each time step. Since we are conducting a steady-state analysis, there is only one time step available. We can add contours to the domain by selecting a contour type from the drop-down menu. We may also add new contour options by clicking on the Draw Contours button. For example, we can add a new contour displaying total head throughout the domain. We may also contour water flow values, material properties, convergence criteria, or custom parameters. In this window, we can add a legend or change the increments and starting and ending values of the contours. Contour labels may be added by selecting Draw Contour Labels and clicking on the desired contour. The label disappears when we click on the contour a second time. Another useful tool in the results view is the Draw Vectors button, which allows you to turn on or turn off the flux vectors that are shown on the domain. Here you can change the maximum vector length or magnification of the vectors. We can add a line depicting the water table by going to Draw Isolines, adding a new isoline, and selecting the water pressure option drawn at a value of 0 kPa. Flow paths may also be added to the domain if desired. These represent the path that a drop of water would travel from the reservoir and through the embankment. After selecting Draw Flow Paths, we can click with the left mouse button to create a flow path anywhere within the domain, and remove it by clicking on the same location a second time. Remember, flow paths are not the same as flux vectors. You can choose what items are activated in the results window at any time using the View Preferences toolbar along the right side of the screen. Here we can toggle results information on or off, such as the flow paths, flux vectors, and contours. Or we can view the mesh, boundary conditions, material properties, or toggle on and off the geometry items, such as the regions or region numbers. There are other options available for viewing result information. View Object Information provides information on each geometry item, such as the boundary conditions applied to a line or the mesh properties of a region. View Result Information provides details for a node, flow path, Gauss region, and so forth. This information includes coordinates, pore pressure parameters, water flow parameters, material properties, and convergence results, which can be useful when evaluating or comparing results from specific nodes within the domain. A report of the analysis may be generated by going to View, Report. The report is an HTML file summarizing the input data, domain geometry, and other information from the analysis. The Draw Graph window offers a wide range of options for plotting the model results. For a seepage analysis, the conductivity versus matrix suction graph helps to assess convergence of the analysis. This is a convergence type graph comparing the simulated hydraulic conductivity function to the inputted one for each material in the domain. When the two plots diverge, the analysis has convergence issues. To create a new graph of the pore water pressures through the middle of the embankment, we will go to Add and select Pore Water Pressure, Water Pressure versus Y from the drop-down menus. We will then click on Set Locations to choose which nodes to plot the results from. If we change the Select option to Geometry items, we can choose a region, line, or point. Multiple geometry items may be selected by holding down the Control button while clicking on the left mouse button. If we use the Custom Location Selection option, we can choose any node within the domain. We will select the nodes running through the center of the dam by holding down the left mouse button and dragging a box across the desired nodes within the domain. Alternatively, we can press the Shift button while using the left mouse button to click at the start and end of a line. The selected nodes are where this line intersects the finite element mesh. Once the desired nodes are selected, we can go back to the Draw Graph window by pressing Show Graph. The More button in the Draw Graph window provides the following options: to copy the graph as an image so it can be pasted as a picture in another program, to copy the graph data as tab-delimited columns which can be pasted into other software like Microsoft Excel, or to export the data to a comma-delimited file. Under Options, we can change the visualization of each plot by customizing the labels, changing the scale of each axis, rotating the graph 90 degrees, adding or removing the legend, or changing the line style. Let's say we want to know what would happen to the phreatic surface given the presence of a tow drain. We can do so by creating another analysis in the Definition view, in the Define Analyses window. Here, we will clone our current steady-state analysis so that the material properties and boundary conditions are copied to the new analysis. When we do this, a second steady-state seepage analysis appears in the analysis tree. We will change the name of this new analysis to indicate that it includes a drain. Multiple analyses may be added to the analysis tree, allowing us to solve multiple scenarios within the same project file. The geometry of the domain is considered project-specific, but the analysis type, material properties, and boundary conditions may be modified. We will change the boundary conditions of our new analysis to represent the presence of a tow drain. First, we will add a point indicating the drain extent, such that the line between the new point and the toe of the dam represents the drain's position. We then must add a boundary condition along this line to represent the drain conditions. We will go to Draw Boundary Conditions and add the zero pressure boundary condition along the drain line. Next, we will create a finer discretization of 0.5 meters along our tow drain, as our phreatic surface is expected to fall somewhere along this line. We can do so by going to Draw Mesh Properties, selecting the line representing the drain, choosing Length of from the drop-down menu, and entering 0.5 meters as the desired mesh length. Otherwise, we can leave the other analysis properties as they were in the first analysis. We are ready to solve this new analysis. The results view automatically opens since the solved analysis is the one currently selected in the analysis tree. The results settings from the original analysis carried over to the second analysis, so we can see the updated total head contours, flow paths, and the phreatic surface. The tow drain forces water to leave the domain along this line, changing the position of the phreatic surface. There is no longer seepage from the downstream face of the embankment. If at any time you are unsure in your understanding of a dialog box, select the Help tab or press F1 on your keyboard to access the online help. If at any time you would like to view the engineering book for the product you are using and do not want to return to the GeoStudio Start page, you can simply click on the Home button in the online help. Once we are finished interpreting the results, we can view the page layout layer to set up the printing properties of the project file. The page layout toolbar allows for the selection of the paper size, margins, and orientation, the portion of the page in which the model appears called the viewport, and the positioning and size of the model within the viewport. We may also create, modify, or import a printing template. A basic template was created when we selected the page size while setting up our project file at the beginning of this tutorial. That concludes our Getting Started with SEEPW tutorial video. Please see the online help, supporting documentation for SEEPW, and other tutorial videos available on the GeoSlope website for more information. Thank you for watching.